Thanks everyone for joining tonight or today in many of your cases. So as was just mentioned, this is the first time shifted IGS seminar. So we've decided to shift one seminar per month to try to accommodate the cryospheric research community in Asia and India and other parts of the world who have typically had this seminar run in the middle of their night. So we're excited with this opportunity. So for those watching online and others, if this accommodates your time zone better and you're interested in presenting, please feel free to reach out to myself or Tavy Murray, and we can talk about scheduling you in. So today we have two seminars. First, we have MacKie from the University of Florida, who's going to be talking about uncertainty in subglacial conditions with geostatistics. And then we have Vigan Mensah, who's a project assistant professor at Hokaido University in Japan. And he's going to be talking about the freshwater budget of Baffin Bay and the Labrador Shelf. But before we get started, I wanted to pass it over to Hester for a little introduction of MacKie before she starts her presentation tonight.
So thank you, Dave. I just shared my screen. So MacKie is the recipient of one of the two recipients of the 2022 Graham-Cogley Award. So I'm just going to introduce the award. I'm the IGS chief editor of the Journal of Glaciology and the Annals of Glaciology. So the Graham-Cogley Award is a joint award between IGS and IACS. And it was established in 2019, like soon after Graham-Cogley died. And Graham-Cogley made substantial and enduring contributions to glaciology, mostly to mass balance, but he was very instrumental in very large, like global initiatives, and and he mentored a lot of young people. And he was also the chief editor until his untimely death in 2018. So this award was initiated by the Cogley family, and it includes some award money, so that is sponsored by the family. And in even years, when 2020 was the first year, 2022 is the second year, the IGS gives out 2 Graham-Cogley Awards to students who have published papers of exceptional quality in the Journal of Glaciology or the Annals of Glaciology. So for the 2022 Graham-Cogley Award, we had 123 student-authored papers that were published in the 2 years before that. So from that, the associate chief editors, of which Ralph Grave is one, who is also in attendance of this seminar. So we shortlisted 13 papers from 6 countries. And you can actually see the entire procedure, how it all goes on the IGS website. So from these 13 shortlisted papers, we actually have 2 Graham-Cogley Award recipients, Dominic Farner and Emma MacKie. So MacKie is actually talking today in the seminar, and Dominic will talk on, I think, April 10th in the seminar, also at the new time. So these are the 2 papers for which they were awarded the Graham-Cogley Award, and both papers are really exceptional in depth of analysis, in quality of presentation, and in the overall impact. So congratulations to both of them. So this is not the first time that it's been announced. We announced it on the CRIA list as well. So what do they get? Well, they get an award certificate, actually a paper one, printed on very nice kind of shiny paper. They get award money, which is equivalent to 500 Canadian dollars, and that's sponsored by the Graham-Cogley family. They are recorded like online in the IGS award recipient list, and they present in the IGS Global Seminar Series, and their paper gets like promoted a little bit more online than otherwise. So before I give it over to MacKie, I actually want to just list like the other, like 11 other nominees. So we shortlisted 13, 2 were winners. So this is page 1 of the 11 nominees. And there's actually one from the group in Hokkaido too. So Ken Kondo was shortlisted. And And then the second page of the shortlist are these papers. And it really varies from like snow research, sea ice research, ice sheet research, glacier research, geophysical techniques, and everything like that. Okay. So I will stop sharing my screen, and I have the honor to introduce MacKie, and she will talk about uncertainties in stochastic or quantifying uncertainty in subglacial conditions with geostatistics. So,
awesome. Well, thank you for that introduction. It's nice to be here, and of course, I'm no longer a student, so today I'm going to talk a little bit about the stuff that my lab is doing and my current students are doing that was based on this paper that I published in JGLAC a few years ago. So I'm now an assistant professor at the University of Florida, and I'm the PI of the Gator Glaciology Lab. And I'm going to talk about some of the ways that we're using geostatistics and the methods that I sort of first developed as part of this JGLAC paper to continue our mission in better characterizing subglacial conditions and being able to quantify uncertainty in those conditions. So I have a number of amazing students in my lab who are working on using geostatistics and doing uncertainty quantification in different ways. And we're really interested in better resolving this ice bed interface and characterizing the geology, hydrology, and topography at the ice bed interface and figuring out how that influences ice sheet dynamics. But one of the challenges in representing basal conditions is figuring out how to represent the ice bed interface, especially the topography, in a way that is geologically realistic, as well as obeys any geophysical constraints that we have. So right now, all of our bed measurements are primarily based on ice penetrating radar data. So say we have some true topography that looks like this, and we have some sample flight lines. We have to interpolate that data to create the continuous digital elevation models that we use as inputs in virtually any analysis of the bed. The problem is that interpolation can give us kind of a biased view of what our bed topography looks like. Most methods are designed for accuracy and can create some sort of smoothing in our representation of the topography. So say we've got some cross-section of the bed topography, and these blue dots represent measurements of the bed elevation. And we want to interpolate that somehow. Most people, I think, would think about trying to find the most accurate elevation value at any given point, which would look something like the red line here. And that gives us a very smoothed bed representation. So the problem with that is that the way we represent the bed is not realistic, not geologically realistic. So we're losing important textures that exist there. And then, of course, we also compromise our ability to quantify uncertainty. Alternatively, we can use geostatistical simulation to generate many different representations of the topography. So that's represented by these black lines. And each of these realizations is an equiprobable realization of the topography, and they're designed to reproduce the spatial statistics of observations. So each of these is less accurate in a least squares sense than your red line, but more realistic in a geological sense. And this ensemble quantifies your uncertainty. So you could imagine running some sort of ice sheet model or analysis on each of these realizations, and using that to understand how your uncertainty in the bed topography propagates forward. And this kind of thinking has been widely used in oil and mineral exploration applications. So this idea has been around for a long time because they figured out early on that the subsurface heterogeneity is so important for things like fluid flow. And you can use it to quantify your uncertainty and make better decisions about where to extract natural resources. So my group is all about extending this philosophy to glaciers. One of the main ways that we can quantify spatial statistics is using something called the variogram, which measures your spatial covariance of your measurements. So let's say we've got some unknown topography here, and we've got some data points that measure the bed topography. You can imagine that two measurements that are close together are more strongly correlated, and measurements that are farther apart or have a bigger lag distance are less correlated. So we've got the separation distance of pairs of points here and the variance on this axis. So pairs of measurements that are further apart have a greater variance. And we can, average across those pairs of measurements with the same separation distances to construct something called the variogram, which measures the degradation in spatial correlation of measurements as they become further apart. So we can use that to quantify our spatial statistics and characterize the roughness of our topography. And we can use that variogram to enforce those statistical properties on our simulated topography. I usually use a simulation tool called sequential Gaussian simulation. And the idea behind this is that, say you have some unknown topography with some measurements, you use all your variogram statistics to construct some probability distribution of where you think your topography should be there. Mm-hmm. Now, if you were doing a deterministic interpolation approach like kriging, you would sample the mean from this distribution. But because we're doing geostatistical simulation, we randomly sample from this distribution, and that becomes our simulated value. And then we treat that as an exact measurement, and we repeat the process over and over, filling in random grid cells until we've populated the entire domain and created a continuous geostatistical simulation. So this figure is actually a modified version of what I had in my JGLAC paper that won this award. This is an example from that same paper where I applied this approach to Jakobshavn Glacier in Greenland. And here I actually, I accounted for the correlation between these measurements with bed machine topography. So in this region, bed machine uses mass conservation to, better kind of constrain some of the morphology and the fast flowing areas in the channel. And I wanted my geostatistical simulation to use that information. So I used a method called sequential Gaussian co-simulation, which accounts for the correlation between these measurements in bed machine. And then it generates simulations such that the simulated topography replicates the correlation between this data and bed machine. So it gives us a little bit more of a refined simulation. And for this study, I was interested in figuring out how uncertainty in topography affects uncertainty in the subglacial hydrology. What we were able to do was we generated many hundreds of these realizations and applied very simple water routing models to each of them. So here's bed machine, and here's the water routing model for bed machine, and here are some example simulations and the different water routing models for each of those. And unsurprisingly, small differences in the topography can have a big effect on the downstream modeled subglacial hydrological channels. I've highlighted a couple areas here where the channels look pretty different. So this is showing that, of course, our water routing models are very sensitive to the topography, but we can use this approach to visualize our confidence in different channels and take an average across each of them. I actually don't have a figure of my average model across all of these, but one of my former lab mates, Riley Kohlberg, made a cross stitch of a figure from this JGLAC paper that is on my wall in the round hanging behind me. So that figure from this paper has been immortalized in my home office. But anyways, yeah, so this was all published in JGLAC, and I was very excited that this got an award, because I did kind of go out on a limb with this and have really been exploring what geostatistics means for our understanding of subglacial conditions. More recently, I worked with some ice sheet modelers to explore how ice flows over different types of surfaces. So here we applied an Elmer ice sheet model to a very small patch of high resolution topography, also at Jakobshavn Glacier. So the resolution here is about 25 meters. And comparing bed machine and simulated topography, we see that with smooth topography, there's a bit more of a plug flow behavior. Whereas with the simulated topography, we have a lot more friction and deformation heating, and the development of a pretty thick temperate layer of ice near the bed. And there are actually borehole measurements in this region that show that there is a thick but also very highly variable temperate layer near the ice bed interface. So by incorporating this rougher topography into our ice sheet models, we can potentially more accurately characterize how ice is flowing here. So I think there's a lot of good reasons to incorporate more geostatistics into our analyses of the subglacial environment. However, there are a lot of issues with accessibility when it comes to geostatistics softwares, because these methods were primarily developed for the oil and mining industries. And they have a lot more money than we do, and work with different types of data sets. They usually work with boreholes, whereas we have very large remote sensing data sets. And they're designed to be used by like expert users. And you know, not for ice sheet applications. So I pretty quickly hit kind of a ceiling with the kind of science I could do with the tools that existed. So I recently made a geostatistics software in Python called GStatSim. So here's some bed elevation data from Greenland, and about a dozen different ways to interpolate that same data set using a number of different geostatistics algorithms. So we've developed some open source tools so that anybody can replicate the results from my JGLAC paper or develop their own workflows. We also have some tools for ways to account for differences in roughness in different areas. So here I arbitrarily broke up the domain into 3 different clusters and just assigned fiddled with the dials and assigned different roughnesses to different places, and we can create seamless maps with different roughnesses. Here we made a density-based clustering algorithm to group different areas to quantify different roughnesses in these regions. We can also incorporate secondary constraints, much like I did in my Jakobshavn paper, where we have some other variable that has some correlation with our topography or whatever it is that we're interpolating. So for example, here, if the ice surface has some correlation with the bed, we can interpolate these measurements such that it maintains that correlation. And then we also have a number of different functionalities for quantifying your spatial variance. You know, there are many different geological phenomena that have different types of textures. And so we have tools for capturing those different textures. And then if none of this made sense to you, we created an educational Jupyter book. So this is like a kind of a Python e-textbook with scripts where you can download tutorials, and we tried to explain some of the theory and the math and parameter selection so that it's easy for anybody to spin this up. One of the challenges with geostatistical simulation is that it's generally very slow because you have to simulate each grid cell one at a time, so it doesn't scale well. But to help address this, one of my undergrads recently published a first author paper showing how we can use different processors or CPUs to perform these simulations in parallel and significantly cut down on the computational time. So here's an example at Pine Island Glacier. So we're working on improving the speed of these algorithms so that ultimately we can run this at ice sheet scales. And I've had this acronym going for many years called Demogorgon, or Digital Elevation Models of Geostatistical Origin. And we're hoping to be able to do this across Greenland and Antarctica. However, if you're an ice sheet modeler, you might be thinking, what about mass conservation? How do we incorporate ice flow constraints into these simulations, which is going to be super important if we want to use this in ice sheet models. In case you're not familiar, mass conservation is used to enforce some physical constraints on what the topography can look like, such that your modeled ice surface and ice surface velocity matches that of observations. So usually this is solved for using like an inversion, but geostatistics or simple geostatistics doesn't account for this. And we have a similar problem here with sub-ice shelf topography, where gravity inversions are typically used to estimate this, but of course there's a lot of smoothing that goes into solving these inversions. And this gets at kind of a bigger challenge with performing geophysical inversions. If we have some model of the Earth, we can usually forward model what the geophysical response should look like. And that's the forward model. And that's usually pretty easy to do. This is generally a deterministic model or something that has a unique solution. But going the other way is more challenging. There are usually like an infinite number of Earth models that could explain your geophysical response. And we usually, and even though this is a non-unique problem, we usually force it to have a unique solution in order to make this problem more tractable. And that creates a lot of smoothing in our representation of that solution. But we can actually use geostatistics to help us solve inverse problems in a way that is realistic. And I promise I'm wrapping up in a minute. And we can do this in a Bayesian framework using a sampling approach or using Markov chain Monte Carlo. And the idea is that you randomly perturb your model of the Earth or your topography and forward model the geophysics until you converge on some model that matches your observations. So for example, with in the case of topography, we can perform some simulation, compute the forward model, perturb it, recompute the forward model, and then accept or reject that change, depending on whether or not it improves our fit to observations. So one of my current PhD students has done this using mass conservation. So this is bed machine here. This is Denman Trough in Antarctica. Here is sequential Gaussian simulation, so geostatistics using no physics. And here is the Markov chain Monte Carlo mass conservation inversion that uses geostatistics. So now we can account for both the physics and the geological realism here, and generate multiple simulations to quantify uncertainty. Another one of my grad students is doing something very similar for performing a gravity inversion under the Thwaites ice shelf. So using this kind of geostatistics Bayesian framework, we can combine the benefits of geophysical inversions with geostatistical simulation and provide representations of the bed that are both physically constrained, but also sample our uncertainty space and have the right textures. And ultimately, we can use that to strengthen our hydrological modeling, understanding of basal sliding processes and ice sheet models, and quantify our uncertainty within those models. So with that, I will close and take any questions.
Great. That was really interesting. Any questions for MacKie? Yes, Vigan.
Hi, Mickey. It was very nice talk, very clear. I'm not at all a glaciologist, but I could understand what you said, so it was nice, very nice. I just wanted to know, what is there a sampling interval in the original data that is needed, a minimum sampling interval, so that the model can actually work? And let's say if there is less than one sample per 50 kilometers, the simulation cannot work. Is there something like that?
No, our simulations will still work. They'll just, be less accurate. There'll be bigger uncertainties. And the larger scale structure might be less good. But yeah, they'll still work. I think the more interesting question that I'm kind of hoping to, figure out is like, if we can ask the question, like, what's the minimum or maximum spacing that we would need to like answer a certain scientific question or
I see. Yeah.
Model the sea level rise projections with a certain level of fidelity.
I see. Yes, that looks very interesting. Yeah. And so oh yes, there's another question. So I will.
Interesting. Yeah, Roland.
Hi. I don't know if you can hear me. I seem to be having some
Yeah,
Zoom
good to see
issues.
you.
Okay.
Are those
Okay.
tessellated pavements or whatever it's called in
Yes,
the background?
that's down near Eagle Neck
Yep.
in southern Tasmania. Yeah.
Saw that last year.
Yeah. Turns out to be quite an interesting feature, the origins of that. I used to play there when I was a kid, and it was just interesting. I had no idea there was some complicated tide-related processes. Anyway, getting to my question. As was pretty clear in your Yakuzavan hydrology example, these simulations and choosing an elevation value, not all locations are equally important or critical in the overall character of the system. Do you have some way of measuring whether particular locations are particularly sensitive to those broader scale features in terms of long-term consequences? Obviously, you just have a slight fluctuation in what would otherwise be a choke point in one of these streams, it can completely change the hydrology.
Yeah. Oh, yeah. That's something I would love to play around with. I think there is a way where you could, where using like the simple Shreve type water routing model that I used in this study, where you could kind of attribute, I don't know, uncertainties in pixels in the water to upstream pixels. I think that could be pretty straightforward to do. For ice sheet modeling, I think that's a more interesting challenge. But I could imagine doing something like running an ensemble of ice sheet models and then looking at like the average of bed topographies for like the high impact scenario versus the low impact scenario, and trying to like look at the difference that way to see if there's certain features in the bed topography that are more conducive to
Yeah, I mean, apart from anything else, would be feasible if you have such an ensemble to offer very useful advice of this is a location where you'd actually better go there and find out what reality is, because different alternate realities have very different characters. Or in other places, I can think of probably large fractions of the interior of East Antarctica. Everything is going to come out more or less right, and it's not going to generate drastic heterogeneity just by changing one or two values. Anyway, thank you.
Yep, yeah, that's a really on the nose question. Cool. Well, I think I'll mute myself then. Thank you.
Sorry, I've got a crying kid upstairs, so I'm trying to stay muted. Any other questions? Any other questions about how long it took to find the acronym Demogorgon?
Oh, this is a pandemic baby. It's going to take a decade to get it going, but I had the acronym way early.
Okay, perfect. Well, great. Thanks, MacKie. That was an excellent talk, and congrats again on receiving the Graham Cogley Award. It's quite the honor. So yeah, fantastic talk, and thanks for accommodating this so late at your time. So with that, we'll switch gears to the other side of the cryosphere. We're going to go to sea ice, and it's not part of the cryosphere, but it's sort of an add-on, but freshwater in Baffin Bay and over the Labrador Shelf. So, Vigan, I'll let you take it away.
Okay, and thanks a lot for the introduction, Dave. So it's going to be a ocean talk. So I hope that it's going to be clear enough for all of you. So I'm Vigan Mensah from Hokaido University, and I'm going to introduce this work that we have done together with researchers from Nagoya University, Fujita-san, and from Environment and Climate Change Canada with Stefan Howell, and then students and staff from Hokaido University. So it's about the Baffin Bay and the Labrador Shelf, freshwater budget, and how it is influenced by glacier and sea ice melting. So let's start first by looking at this map of the ocean circulation in the North Atlantic and in the Baffin Bay here and the Labrador Sea and Labrador Shelf here. We can see that we have a system of current entering into the Baffin Bay and then exiting through the Labrador Shelf and going all the way to the North Pacific Ocean, North Atlantic Ocean. Sorry, I used to work on North Pacific in Japan most of the time. So what's interesting here is that all along the pathways of this current, we have input of freshwater. So let's start with local input sources in the Labrador Sea and the Baffin Bay. We can have glacier or river outflow or sea ice, as we are going to see later. And on top of these local sources of freshwater, we also have remote sources. For example, we have freshwater exported from the Arctic Ocean through the Fram Strait, freshwater coming from the East Greenland Glacier, and all this is also transported towards the Baffin Bay and the Labrador Sea or Labrador Shelf. Same from water coming from the Beaufort Sea, freshwater, and going through the Nares Strait or the Canadian Arctic Archipelago through the Baffin Bay and Labrador Sea, or water, freshwater coming from the Hudson Bay, which is also a big reservoir. So when we look at this map and at these blue and yellow arrows, we understand that actually the Baffin Bay and the Labrador Shelf, they are kind of a channel for freshwater to go from polar and subpolar region all the way towards the North Atlantic. So in a situation where climate is changing and we might have a lot of excess freshwater coming into this region, it is really interesting and necessary to know what changes affect both the local sources of freshwater and also the remote sources of freshwater. Let us first focus on the local sources of freshwater in this 3D map of the Labrador Sea and the Baffin Bay with the Narrow Strait to the north here. First, we have sea ice, which is generated in winter, it drifts, and it melts in summer. We also have sea ice actually coming from the Narrow Strait, from the Arctic Ocean through the Narrow Strait, arriving in the Baffin Bay and drifting south and melting all the way. Then we have glacier along the west coast of Greenland and also along Baffin Island or Devon Island. We have river runoff. For example, here we have the Churchill River in Newfoundland. And we have, of course, precipitation. So most of these freshwater sources, local freshwater sources, are inputs in spring and summer, which makes that throughout spring and summer, we have a layer of fresh water on top near the surface in the Baffin Bay and along the Labrador shelf. So we want to know how does this change over the past 50 years? That is one of the big questions. With a lot of warming, so what is happening with fish freshwater sources? So the first thing that we are going to do in this study is to calculate what I call the summer freshwater volume, so SFV, or summer freshwater thickness, SFT. So we are going to use ocean data of temperature and salinity to estimate that. And we are going to do intercomparison by calculating the freshwater budget from independent measurement or estimation. That is the first and the biggest part of this study. The second part is that we also want to know what happens to the remote freshwater sources. So the ones which are not originally not from the Baffin Bay and Labrador Sea. For that, we are going to estimate the freshwater content. So summer freshwater volume and freshwater content are different quantities, but they can be both estimated from temperature and salinity ocean data. And we are going to do some comparison here. Okay, so let's first take a look at how we build the freshwater budget first. So we look at this table, we have 3 colors. So we just focus on the 3 colors. The main message is that we have 3 main parts of our freshwater budget. We have the part which is coming from sea ice. How much freshwater comes from sea ice? And this can be estimated from satellite sea ice data, sea ice thickness, or as well as SAR images. Then we have another part about the glacier melting, which is obtained by energy mass balance model, and the iceberg calving, which is obtained by the well-known product by Mankoff et al. And the last part is how much precipitation do we have. So we have the ocean part, which is obtained by the analysis product, and the river runoff, which is obtained also by an energy balance model by Fujita and Sakai. So we can do a freshwater budget with that. The next question is, how do we use ocean data to estimate the summer freshwater volume? And for that, we need to understand what happens in the ocean between winter and summer. In winter, we have a lot of wind, we have a lot of generation of sea ice at the surface, and our water column in the top 100 meters is well homogenized. The temperature in black is near the freezing point, around -2 degrees, and the salinity in blue is relatively high and also very homogeneous. But then comes spring and summer. We have atmospheric warming, so the temperature starts to increase. And because of that, let's say the sea ice is melting. So with the release of fresh water at the surface, we have a much lower salinity at the surface. And below that, we still have the winter water, cold water here. So the purpose of the methodology is to automatically detect the layer of fresh water near the surface. We call that the salinity deficit. We just need to detect that. And once we have detected this layer, we use a mass balance formula to convert this delta S into freshwater thickness. So now we know how to do it, and we are going to use all the historical data which have this signature of freshwater at the surface and cold water below. So we take all the data between May and September, and that's about 50,000 profiles. And we only select the data with the freshwater signature on top and the cold water below. This is around 12,000 profiles. And I have plotted in color here the salinity of these 12,000 profiles in our region here. So now that we have our profiles, we have our formula, we convert our profiles or salinity deficit into a summer freshwater thickness distribution. That is what we have here. And we make a climatology from that. And we obtain about 2,000 cubic kilometers of summer freshwater volume throughout our study area. So let us compare this climatology with that of the maximum winter sea ice thickness. And if we look at a first glance, there is an overall match between the two climatologies. That is, the maximum freshwater thickness is located at the same locations as the maximum sea ice thickness. We have lower values along the Newfoundland and Labrador coast in both cases, and we have very low values along the coast of Greenland. But if we look a little bit closer, we can see influences of other freshwater sources. For example, along the coast of Baffin Island, we have very high values of freshwater thickness, which could be due to the glacier melting. Same here in the southwestern part of Greenland. Okay. Then second, we have the effect of river. For example, here we have the Churchill River, which outflow freshwater from here, and we can see here that we have kind of a larger value of freshwater along the pathway of the Churchill River plume. Third, we can see that in the northern Baffin Bay, we have a much higher freshwater thickness compared to the sea ice thickness. This might be due to the ice which is flowing from the north, from Narrow Strait, arriving in Baffin Bay and melting there. So qualitatively, it looks like our methodology enables us to distinguish between different kinds of freshwater input. So what about quantitatively? For that, we need to look at our freshwater budget. We saw before 3 colors, 3 parts. Sea ice represents about 40% of the freshwater budget. Glacier is about 20%, 25%. And then we have the precipitation minus evaporation. We can see in this proportion that sea ice and glacier are big contributors to the freshwater budget in summer. And the total volume of these 3 components is 2,330 cubic kilometers, which is fairly close from what we have in our climatology. So both qualitatively and quantitatively, our methodology yields reasonable results. So now we want to understand the effect of climate change. So what we do is that we make a climatology before 1995, and we make another climatology for the data after 1995, and we estimate the difference in blue and red color. And at the first glance, what we see is that Overall, in the Baffin Bay, we have an increase of freshwater thickness. It's mostly red. And in the Labrador Sea, we have a decrease in the freshwater thickness. So now let us separate our region properly. This is a Davis Strait, and Davis Strait separates the Baffin Bay on the north, and we have an increase of 136 cubic kilometer. And the Labrador Sea in the south with a decrease of minus 36 kilometer. But actually, if you look north of south of, let's say, 62° north, we have more than 120 cubic kilometer of losses of summer freshwater thickness for just this area. So we have big changes. So let us see first what is happening in the Baffin Bay. For that, we analyzed the time series from our freshwater budget. We look at the time series of evaporation minus precipitation minus evaporation, sorry, in green, glacier melt and iceberg calving, and we calculate the average before 1995 and after 1995. For P minus E, we get only minus 3 cubic kilometers. Basically, it does not change. However, the iceberg calving has been increasing strongly, especially after 2005, plus 55 cubic kilometers. And the glacier melt has been increasing a lot more, with more than 134 cubic kilometers. So we remember that in the Baffin Bay, we have an increase in the volume of freshwater of plus 136 cubic kilometers. So we can say that glacier melt and iceberg calving are largely responsible for the increase of freshwater thickness in the Baffin Bay. So now let us take a look at the Labrador Sea, south of the Davis Strait. Because we have a lot more data here, we can actually make a nice time series, as you can see here. And if we look at the first glance, there doesn't seem to be great change. But if we separate and we calculate the trend before 1996, before 1995, and after 1995, we can see that we have large differences. Before 1995, not much happening. The trend is almost zero. But after 1995, we have a decreasing trend of minus 82 cubic kilometer per decade. That is 10% of decreasing of freshwater thickness per decade, which is very large. So we want to understand what's happening here. So we are going to zoom in a little bit in this last 30 years of data. And we are going to compare this time series with the different time series from our freshwater budget. And actually, there is only one time series which is well correlated with our summer freshwater time series, and that is sea ice. So here I have the time series of sea ice from the proxy sea ice thickness product by Glissener et al. And it shows a decreasing trend of 72 cubic kilometer per decade. And this is very close from the trend that we have from our freshwater thickness or volume in the Labrador Sea. We also have a fairly good correlation between the two time series with about 0.45. So at least we can say that the decrease of sea ice volume in our study area plays a significant role in the decrease of the overall summer freshwater volume in the Labrador Sea. So let us make a short summary for this first part of the study. We estimated the freshwater thickness and volume from ocean data in the Labrador Sea and Baffin Bay, and this is consistent with the freshwater budget. In the Baffin Bay, we have an increase of the freshwater volume over the past 30 years, which is likely due to the enhanced glacier melting and iceberg calving. in the Labrador Shelf, we have a decline in the past 30 years, which is likely due or related to the loss of sea ice volume, mostly in the Baffin Bay, actually. So now let us look at the much shorter second part of our study. Right now, we look at the local sources of freshwater. Now we want to know, what about the changes in the remote freshwater sources? We know that some freshwater could be coming from the Baffin Gyre, some from the Hudson Bay, and some from the eastern part of Greenland. And these freshwaters, they travel several thousands of kilometers, and it takes many months for them to come in our region. So they may not necessarily have a clear surface signature. It may be well mixed over a large depth. So to estimate that, we need to use a different method, and we are going to estimate the freshwater content. What is the difference between the summer freshwater volume and the freshwater content? That's what we are going to see here. For the summer freshwater volume, so everything that I showed before, we just need to find the salinity deficit near the surface. For the freshwater content, we just use a fixed salinity reference of 34.8, and we consider as freshwater anything that is fresher than this value. So the freshwater content includes both the summer freshwater volume and also the remote sources of freshwater. And now we are going to compare the time series of freshwater content in red and the time series of summer freshwater volume in blue. So blue is everything that I showed before, and red is everything that I calculated now. And what we see is that first, the trends are opposite. Over the past 70 years, we have a weak decreasing trend of summer freshwater volume in blue. But in terms of freshwater content, we have a strong increasing trend. The second thing that we notice is that before 1996, the two time series are well correlated. It's 0.71. Actually, if I remove the trend, the correlation increased to 0.81. So the two curves are very well correlated, which means that the freshwater content before 1996 depends essentially on the local sources of freshwater in summer, glacier melting, the sea ice melting, and so on. But after 1996, the two curves are not well correlated. It drops to 0.42, and we can see that there are large differences. That means that after 1996, we have other sources of freshwater which come and which become dominant in our freshwater content variability. So that is the main thing to remember. Before 1995, freshwater content basically equal summer freshwater sources by local sources. After 1996, we have additional sources of freshwater which comes in into the Baffin Bay, into the Labrador Shelf. That could be either the Beaufort Gyre, because we know that the freshwater content has increased over the past 50 years. It could come also from the East Greenland with the melting of glacier, or from the Hudson Bay. But at this moment, I cannot answer to this question. It's beyond the scope of the study, but that could be a topic for a future study. So that's the end. If you are interested, you can find the manuscript about this study in IGS. The result I presented here are slightly different from the one in the paper because I started to take into account the comments by the reviewer. So that's it. Thank you.
Great, thanks, Vigan. We'll open it up to questions. Yeah, Takanobo.
Thank you very much, Vigan. Thank you very much. Very clear and very interesting talk. And
Thank you.
my question, so can you hear me?
Yes.
Okay. So my question is that, the effect of sea ice. And
Yes.
you only treated the sea ice as a vection from the Arctic Ocean.
Yes. Mhm.
But probably, I think in the northern part of the Baffin Bay, there's a large polynya, north
Yes.
open polynya.
Yes,
And
there's North Polynya. Yes.
yeah. And then that is the largest polynya in the northern hemisphere.
Yes.
And
Yes.
I'm now concerned about the effect of the polynya, the production
Yes.
produced sea ice as a polynya.
Yes.
So
Mm,
how?
absolutely.
Yeah. And
Okay.
have you ever considered about that?
Yes, we did. So, of course, so that part, the part produced by the North Polynya, would be included in the sea ice thickness climatology. And what we did is that we also estimated the transport of sea ice through the Davis Strait. So we have a gate there, and we estimated the ice volume there. And the sea ice which is produced in the North Polynya is going to be transported between throughout spring and summer, roughly. Is going to be transported towards the Labrador Sea. So it is taken into account. And what we think is that most of the sea ice in the Baffin Bay in winter has already been transported in the Labrador Sea and melted there during the summer when we analyze our data. So it is taken into account, yes.
Okay. Thank you, Grace.
You're welcome. Just a small precision. So if I can, why cannot? Okay, just a small precision. So in terms of sea ice thickness, we have about 800 cubic kilometer of sea ice thickness here. But the transport of sea ice from the Arctic is one order less. It's about 90 cubic kilometer it's about 150 kilometers, sorry. So it's quite less. So most of the sea ice that we have here is actually from the one which is produced by the North Polynya. Yes.
I had a quick question. How did you choose 1995 as the breakpoint? Was that based on sort of the evolution of trends, or was there a
Yes.
specific shift in 95 that you were trying to capture?
Yes, so I think I need to recheck in the papers. I explained it, but yes, it's based on the trends in sea ice extent, and so there is a paper which describes that in the Arctic Ocean, especially in the Baffin Bay, we have a stronger trend after 1995 in terms of sea ice extent, decreasing trend after 1995. So that's why I choose 1995 as my limit.
Okay.
So
Interesting.
it was mostly based on sea ice rather than glacier or other things. Yeah.
Yeah. Anything else? We have time for one last, just as my clock here flips to the top of the hour. Nothing else. All right. Oh, Hester, yes.
Yeah, I have a quick question because I'm looking at the increase in the freshwater amount, like in front of the coast of the Baffin Island on that
Yes.
side that you explained, because there's so many glaciers. But there's also export of sea ice from the Lancaster Sound there, which is like very much like wind related, and it can really vary per year. And I've kind of heard that it's one of the few regions where there's like a bit of an increase in the exports there. So how do you know that it's actually from the glaciers rather than from sea ice export from the Lancaster Sound?
Yes, so it's a very good question, and I would say it's more, maybe it's an order of magnitude, I think. So we estimate that in summer, there is a strong increase, it is true. The largest increase is mostly for the Narrow Strait. We do have an increase as well in the Lancaster Sound, but we estimate that between May and September, maybe the additional inflow of ice would be about 40 cubic kilometer. And in terms of glacier, we have above 67 degree north. So really, mostly the northwestern Greenland and also the Baffin Bay Greenland. We have 155 kilometers. So I'm not complete. I cannot say, oh no, it's not a sea ice from Lancaster Sound, but it seems quite reasonable that because the glacier melt has increased much more compared to the sea ice export. This kind of increase of meltwater thickness in the Baffin Island coast are more likely to be due to the melting of glacier.
Yeah, so thanks. That's explained really well. It's just the budget, you know. You only have so much here, and if you, okay. Thank you.
Welcome.
Okay, thanks for that. Okay, so we'll wrap it up there. So thanks to both of our speakers tonight, both great talks. As per usual, this has been recorded and will be posted on the IGS YouTube page sometime tomorrow. So yeah, thanks so much. I just quickly wanted, before we end, next week we have Guillaume Jouvet on a glacier evolution model that's boosted by deep learning. And the next shifted time zone or seminar is going to take place on February 29th. We're still looking to confirm a speaker for that. We have a few options, including somebody on this call, Ralph, who has emailed me separately. And because he's on the call, I was just going to promote that Kei Oshima is going to give a talk in the shifted seminar on May 16th. And so we can look forward to that, where we can learn a lot more about ice production in the North Water Polynya, I'm sure. So with that, we'll wrap it up. Thanks, everyone. Take care. Have a good day. Have a good night wherever you are.
Thanks.
And, take care.
Thanks a
Good
lot.
night.
Bye.